Hello everybody. Today we will discuss about the designing of the FIR filter. So whether the voice is audible
Yes, sir.
and quickly visual. Na?
Yes, sir.
Okay, thank you, madam. So here before the discussion of the designing of the IIR filter, again we will try to cover some concepts of the digital filter. As we know, if we are interested in order to design the impulse filter, then first of all the requirement is considered. And as we know, the impulse response corresponding to each of these non-causal filters are infinite in length. Hence, these filters means ideal filters are physically not realizable. In order to realize these filters, there is a need of the truncation. And truncation is done with the help of the different methods. A transition band is specified between the pass band and stop band to permit the magnitude to drop off smoothly here, and the magnitude response specifications of a digital filter in pass band and in the stop band are given with some acceptable tolerances. So these are the three parameters which are introduced during the time of the specification of any filter from the ideal condition to the practical approaches here. And as we know, if we consider here the graph and say this is the typical magnitude specifications for a digital low pass filter, then we will find that ideal low pass filter looks like something in this manner. That is, it has a pass band of the gain up in the pass band is 1, and at the pass band age frequency it suddenly drops to the 0 here. But in the case of the typical magnitude specification, we have to consider a range of the ripples in the passband, and this range of the ripple is considered from in the range that is -1 minus delta p to 1 plus delta p. That is delta p towards the positive side and the negative side. And this delta p is known as the peak ripple value here, and the negative peak ripple value is represented here the minus del p. And there is a gap between the pass band and stop band. It is known as the transition band, and then starts the stop band. In the stop band, again there is a range of the ripples that is defined in the stop band. And the pass band is frequency is described by the omega p, stop band is frequency is described by the omega s here. Now, if we if we are interested in order to describe the same specification in the mathematical model, then we can describe the passband by this one, that passband exists for the value of the omega starting from 0 to omega p, and error bound is in this band is plus minus delta p, and magnitude exists, that is the mod of the g e to power j omega, it exists between the ranges 1 minus delta p to 1 plus delta p if omega mod of the omega is less or equal to omega p. It is the specification of the passband. Similarly, we can describe here the stop band. It is defined in the range of the frequency omega s to the pi, and error bound in this band is del s, and the magnitude, that is the mod of the g e to power j omega, it is less or equal to the delta s, where the delta s is the stop band ripples, and it exists for the mod of the omega between the range omega s to the pi here. Transition band exists from omega p to omega s. That is the omega s minus omega p will be described as the transition band. Now, the frequency response g e to power j omega of a digital filter is a periodic function of the omega, and the magnitude response of a real coefficient digital filter is an even function of the omega. And omega, that is the digital frequency, ranges from 0 to pi, that is the mod of the omega lies between the 0 to pi here. That is the total ranges from minus pi to the pi here. Now, the digital filter specifications are often given in terms of the loss functions. That is, what is the loss? Attenuation. And attenuation is described by a omega, that is minus 20 log 10 g e to power j omega, and it is described in the dB. the peak pass band ripple, that is the here the alpha p, this can be described as minus 20 log 10 1 minus del p in dB. This is known as the peak pass band ripple here in dB. Similarly, the minimum stop band attenuation, that is the alpha s, this may be described as minus 20 log 10 base delta s, and it will be described in dB here. Now, here the magnitude response specification of a digital low pass filter may alternatively be given in a normalized form. That is here the maximum value of the magnitude in the pass band is assumed to be unity here, because it will be divided by the maximum, whatever is the range that will be described, divided by the maximum value. So the normalized value will become 1 here. The maximum pass band deviation denoted as the 1 upon in under root 1 plus epsilon square is given by minimum value of the magnitude in the pass band. And here the maximum stop band magnitude is denoted by the 1 by A. This is another way of the representation, that is known as the normalized specification. Here in this one, this maximum value is the 1, and this value of the, that is the deviated ripples value at which the ripples has been taken, or the attenuated value is 1 upon 1 in under root 1 plus epsilon square, and this value that starts in the stop band is given by 1 by A here. So maximum value of the magnitude gain is assumed to be unity, or the minimum value of the loss function is 0 dB. Here the alpha maximum, that is the maximum attenuation in the pass band, it is the 20 log 10 in under root 1 plus epsilon square, because it is 1 by this one, so the minus sign will become the plus here, and it is given as the 20 log 10 in under root 1 plus epsilon square in dB, and alpha maximum, this may be described as minus 20 log 10 1 minus twice of the delta p, that is approximately twice of the delta p in dB, that is defined as the maximum pass band attenuation here. Now maximum pass band attenuation alpha max is defined as the 20 log 10 in under root 1 plus epsilon square in dB, where delta p is much less than 1, and it is typically a typical case, and it can be shown that alpha maximum is approximately near about minus 20 log 10 1 minus twice of the 2 del p, that is approximately equal to the twice of the alpha p in dB here. The pass band and stop band edge frequencies in the most applications are given in hertz, so they have to convert it into the here the radian, and that is in angular edge frequency, and how they will be converted using this concept, that is the omega p is given at the capital omega p divided by the ft and or the fs, and this is equal to the twice by fp divided by ft or the fs sampling frequency, and this may be written as the twice by fp multiplied by t is the sampling time period here. Similarly, omega s may be described as twice by fs multiplied by the t here. Pass band is frequency and the stop band is frequency, and here we have considered ft for the sampling frequency. In order to make a difference between the pass band, this stop band and the sampling frequency, we have considered the sampling frequency, or we have denoted the sampling frequency by the f of the t here. Now the selection of the filter type. The first step is the specification, and after the specification, the next step is to decide the filter type or the design method, means whether we are interested for the FIR filter or the IIR filter. The objective of the digital filter design is to develop a Fourier transfer function, that is the SZ, and that meets each and every specifications of the filter which has to be designed. Now, for IIR digital filter design, the transfer function is a rational function of the z to power minus 1, and it may be represented something like in this manner, that is the Sz having the polynomials up in the numerator and polynomials in the denominator, that is P0 plus P1 z to power minus 1 plus P2 z to power minus 2 and so on up to the Pm z to power minus m, and divided by the next polynomial in the denominator, that is the D0 plus D1 z to power minus 1 plus D2 z to power minus 2 and so on up to the last value, that is the Dn z to power minus of the n here. Hz must be a stable transfer function, and so in order to design the filter, and reduced, it must have the reduced computational complexity. Means the complexity should be as possible as possible here. It means we should try to minimize the order of the filter here. We will prefer to design the lowest order of the n here. Now for FIR filter design, the transfer function is a polynomial of the z to power minus n, and it is described as summation n is equal to 0 to n hn z to power minus n. For reduced computational complexity, means in order to reduce the complexity, the degree n of the hz must be as smaller as possible here. In addition, if a linear phase is desired, then FIR filter coefficient must satisfy this condition, that is the Hn must be equal to plus minus H capital N minus N, where capital N is the order of the filter that has to be designed. If this is the condition that is satisfied, then we say that the filter is which type? That is the linear phase response filter. Now we will describe here some advantages of the FIR filter. Since in the FIR filter there is no feedback, it means the filter will be always stable and it can be designed with exact linear phase. So these are the advantages which are associated with the FIR filter, but there are some disadvantages also. That is, in order to get the same specification or the same performance of the filter, the order of the FIR filter must be much larger than that of the IIR filter. In the cases the order NFIR of an FIR filter is considerably higher than the order of the IR filter of the equivalent having the equivalent performance filter meeting the same magnitude specifications. It has been shown that for most practical filter specifications, the ratio n of the FIR and n of the IR is typically of the higher order, that is of the order of the tens or more than this. As a result, the IIR filter usually is computationally more efficient. Now, if the group delay of the IIR filter is equalized by cascading it with an all-pass equalizer, then the savings in the computation may longer be that the significant value here. In many applications, the linearity of the phase response of the digital filter is not an issue, making the IIR filter preferable because the lower computational requirement. If there is lower computational computations, it means it will be efficient. So efficient performance will take place in the case of the IIR if we are not interested for the linear phase response. Now, the approach to design the IIR filter based on the conversion of a prototype analog transfer function to a digital transfer function is widely used, and then the most common practice of the IR filter design is to convert the digital filter specification into the analog low pass prototype filter specification. Because if we are interested in order to design in a digital low pass filter using the approach that filter will be designed in the analog domain, and then it will be transformed into the digital domain. Then whatever is the specification in the digital domain, that will be converted to the analog low pass prototype, and then accordingly to determine the analog low pass filter transfer function, we will try to meet these specifications. And to transform it into the desired digital filter transfer function, there is a need of the transformation. For example, bilateral transformation may take place here. Why is this approach used? That first we are trying to design the filter in analog domain, and then we are transferring the design filter into the digital filter. Why we are using this approach here? Now see here, analog approximation techniques are highly advanced, and they usually used closed form solution. And the third one is the extensive tables are available for the analog filter design, means data are given here, and many applications require the digital simulation of the analog system or the analog filter. So these are the reasons based on which we will try to design the filter, digital IIR filter, using the approach that filter will be designed in analog domain, and then that design filter will be transformed into the digital domain. What are these? Here the approach advantages are the considerable points. The analog approximation techniques are highly advanced. They usually yield closed form solutions. Extensive tables are available for analog filter design, and many applications require the digital simulation of the analog filter here. We denote the analog transfer function with the help of a polynomial of the numerator and the denominator. Both are function of the S, that is the HAS, that is the system function of the filter in analog domain, having a function of the S, is PAS divided by the DAS. And if we are interested, in order to describe the digital filter transfer function derived from the HAS, then this will be described as the GZ is equal to PZ divided by the DZ. This will be in the digital domain, this will be function of the Z, and in analog domain it will be function of the S. And our approach is to derive the transfer function in the analog domain, and then we will try to transform it into the digital domain. Now, the basic idea behind the conversion of an analog prototype transfer function HAS into a digital IR transfer function GZ is to apply a mapping from the S domain to the Z domain, so that the essential properties of the analog frequency response are preserved. Means all the properties will be transformed from the analog domain to the digital domain using a concept of the mapping from the S domain to the Z domain here. The mapping function should be such that the imaginary axis in the S plane be mapping into the unit circle of the Z plane. Imaginary axis of the S plane will be mapped onto the unit circle of the Z plane here, and a stable analog transfer function be transformed into the stable digital transfer function here. The widely used transformation is the bilinear transformation and the impulse invariance method. We will also describe in the next lectures or in the coming lectures the concept of the bilinear transformation, means how the SZ will be transformed into the Z domain in order to preserve all the specifications of the filter. There are a number of the established approximation techniques for designing of the analog filters, and here we will describe 4 widely used techniques, as we have discussed these concepts in the previous lecture, that we will try to cover the approximation technique of the Butterworth approximation, Chebyshev 1, Chebyshev 2, and the elliptic approximation. Then further details of these methods can be discussed in the next lecture. I will try to cover these from the textbooks here. So first we will discuss something about the filter specification, then Butterworth approximation, Chebyshev approximation, elliptic approximation. Then we will try to describe the different types of the filters which has to be designed. That is the high pass, band stop filter designing. First, we will try to design the low pass, and then we will move towards the designing of the high pass, and band stop filters. Now the filter specification, as we have described these concepts in the first section of this lecture, that ideal low pass filter should have a magnitude response of the form shown as in the below, that is flat response having a fixed value in the pass band, having a cutoff frequency of the omega c minus omega c to the plus omega c here. Now in practical cases, the magnitude response characteristics in the pass band and in the stop band cannot be constant and are therefore specified with some acceptable tolerances. A transition band is specified between the pass band and the stop band to permit the magnitude to drop off smoothly here. So during the time of the specification, we have to make the three approximation. The first one is that flat responses are not possible in the pass band as well as the stop band. So in place of the flat responses, either we will introduce here the attenuation or we will introduce here some permissible range of the ripples. And at the same time, here in place of the sharp cutoff, we will introduce a transition band. Now see, this is the typical magnitude specification for an analog low pass filter that we have described in the previous section. That is that it has a range from 1 plus delta p to the 1 minus delta p, where the delta p is the ripples in the pass band. And in the stop band, it has a range that starts from the delta s here. And in the case of the equiripples, all the ripples are same here. And the transition band is between the omega p and omega s, that is in the low pass filter, it is equal to the omega s minus omega p here. Now, pass band defined as the omega in this range, omega, that is the omega to omega p, having a value of the, now we are trying to specify the analog low pass filter in the pass band. What is the magnitude of this one? That is mathematically we can say it is 1 minus del p to 1 plus delta p. In this range, it should be the mod of both sides with the sign of the mod of, and for which range of the frequency, that is the mod of the omega less or equal to the omega p. And stop band defined by this range of the frequency, that is starts from the omega s to the delta, and we will define the value that is the magnitude of filter that lies between here either equal to the delta s or less than delta s in the stop band. And the magnitude of the frequency in the stop band lies from the omega s to the infinity. We are defining the filter in the analog domain here. And the pass band is frequency is the omega p and the stop band frequency is the omega s. These are the mathematical representation of the analog low pass filter, and in the previous slide we have described the graphical representation of the analog low pass filter here. Now here if we see, then we will find that del p is the pass band ripple and del s is the stop band ripple. And if we describe this value in the dB, then it is named as the peak pass band ripple, that is the alpha p, and it becomes minus 20 log 10 1 minus del p in dB, and similarly alpha s will become minus 20 log 10 del s in dB here. And alpha s is defined as the minimum stop band attenuation. The filter specifications are given in terms of the loss functions. As we have described previously, again we are repeating it, that is, it will be described either with the help of the loss function or the attenuation function in dB, which is defined as the negative of the gain in dB, that is minus 20 log 10, here the mod of the HA, that is the magnitude of the this transfer function of the j omega for a particular frequency of the omega here. Now, if we are interested in order to describe the normalized response here, then the normalized response in the analog filter, it exists between the 1 upon in under root 1 plus epsilon square to 1 here. And the minimum value that is in the case of the stop band, it is the 1 by A. That is, it starts from the 1 by A here. And the pass band is frequency is defined by the omega p. Stop band is frequency is defined by the omega s. And it has also been described in the previous section here. And same graphics can be described mathematically by this one. That is, the magnitude lies between this value 1 upon in under root 1 plus epsilon square and 1 when the range of the frequency omega is mod of the omega is less or equal to omega p. And if the range of frequency or the frequency lies between the omega s to infinite, either the positive side or the negative side, then that magnitude of the filter's response is defined by the value less or equal to the delta s. Now the filter, so passband frequencies of the frequency omega p and the stop band frequency omega s are respectively called the passband edge frequency and the stop band edge frequency, or we can say them passband and stop band frequencies also here. The limits of the tolerances in the passband and stop band is del p and the del s, and these are called the ripples. Usually these ripples are specified in dB and termed as the peak passband ripple and the minimum stop band attenuation. These are the different way of the notations and defining the different values in the passband and the stop bands. Now the peak passband ripple alpha s becomes minus 120 log 10 1 minus del p in dB. Peak passband ripples becomes minus 20 log 10 del s. Now, if we consider here the example, let the desired peak passband ripple of a low pass be 0.01 dB and the minimum attenuation in the stop band be 70 dB, then this can be described as that delta p is equal to 1 minus 10 its power minus alpha p by 20, and this is equal to this value here. Similarly, we can describe delta s that is equal to this value here. We have derived this one with the help of the previous definition of the alpha p and the alpha s that are described in the dB. The magnitude square response of a filter is described by this mathematical equation when we use a particular type of the approximation that is named as the Butterworth approximation. And what is the specialty of this approximation? That the Q factor is of the order of the near out 0.707, that is 1 by root 2, and we will get here the flat response in the passband as well as flat response in the stop band, and hence the magnitude squared response of the analog low pass Butterworth filter HAS of the nth order is described by 1 upon 1 plus omega upon omega c its whole power 2n, where the omega c is the cutoff frequency. Now see the graphical representation of the Butterworth approximation. Here we are getting the flat response in the passband and flat responses in the stop band. And if we are trying to increase the order of the filter, see here the example that represents the different graphs for the different order. Then for the n is equal to 2, 4, and 8, if we see, then we will find that as we are trying to increase the order of the filter, we are moving towards the ideal response of the filter here. Means higher will be the order, better will be the response here. And this is again the representation of the same one that is in the but here we have considered the normalized frequency. Now it in the Butterworth approximation, it can easily be shown that at omega is equal to 0, the magnitude are equal to unity, and as a result the Butterworth low pass filter is said to have a maximally flat magnitude at omega is equal to 0. because we have described that the transfer function is given by this one. So when we put omega is equal to 0, this value will become 1. So we can say it is maximally flat at omega is equal to 0. The gain of the Butterworth filter in dB, this can be described by the 10 log 10 mod of the gain, that is h a j omega h square in dB here. At DC, that is at frequency omega 0, the gain in dB is equal to 0 because the total value of this one will become the 1. So this will become here the 0. And at omega is equal to omega c, the gain is described by 10 log 10 1 by 2, that is near about minus 3 dB attenuation at omega c here. Omega c is often called the 3 dB cutoff frequency. Here, since the derivative of the squared magnitude response are equivalently, the magnitude response is always negative. For positive value of the omega, the magnitude response is monotonically decreasing with increasing omega. For omega is greater or equal to omega c, the squared magnitude function can be approximated by this function 1 upon 1 plus omega by omega c. It's whole to the power twice of the n. Because if we see here the transfer function, then in this one, as we are trying to increase the value of the omega, and if the omega is greater than omega c, then what will happen? Naturally, this term, that is the omega by omega c, its power twice of the n, will be much larger than the 1. So it may be approximated by 1 upon omega by omega c, its power twice of the n. The gain at this frequency, that is the omega 2, where the omega 2 becomes the twice of the omega 1, where the omega 1 is much greater than the twice of the omega c. This may be defined by this function here, and after some manipulation we will find that it is near about the minus 6 dB here the attenuation, that the g omega whatever was the gain at the omega 1 frequency minus 6 n type of the dB here. So if we are trying to enhance the frequency here, as a result, the gain in the stop band decrease by 6 dB per octave, or equivalently by 20 dB per decade, for an increase of the filter order by 1. In other words, we can say that the passband and stop band behaviors of the magnitude response improve with corresponding decrease in the transition band as the filter order n increases, which we have shown in the graph of this approximation here. The two parameters completely characterizing a Butterworth filter are the first one is the omega c, that is the 3 dB cutoff frequency, and the second one is the filter order n. These are determined from the specified passband edge frequency omega p, and the minimum passband magnitude will be equal to 1 upon in under root 1 plus epsilon square. The stop band edge frequency omega s and the maximum stop band ripple 1 by a. This may be described something like in this manner, that is when omega becomes omega p. See here the graph. Yeah, this is the graph here, and if we see the mathematical description of the Butterworth approximation, it means when omega is equal to omega s, or when omega becomes omega p, then what will be the value here? See the graph here. When omega becomes omega s, that is the stop band edge frequency. So at the stop band edge frequency, whatever is the value of the gain, that will be the attenuation at the stop band edge frequency, and at pass band edge frequency we will get here the attenuation at the pass band edge frequency here. So, and if we see here the approximation, that is the normalized approximation. Here, this one. In the normalized approximation, when omega becomes omega p, what is the value of this one? This is equal to 1 upon in under root 1 plus epsilon square. And when omega becomes omega s, this value is equal to 1 by a. That's why we are considering these two representations here, that are considered as omega is equal to omega p and omega is equal to omega s. So when omega is equal to omega p, the Butterworth approximation, that is its magnitude is square, it will become 1 upon 1 plus omega p upon omega c, its whole power twice of the n, and that value will become 1 upon 1 plus epsilon square. It was in under root, and here we have considered the square one, so this will become 1 upon 1 plus epsilon square. Similarly, when the omega becomes omega s, at that time this value becomes 1 upon a square. The magnitude response of the Butterworth filter is monotonically decreasing with increase in the frequency omega here. Now solving the above two equations here. Now we consider the logarithmic log towards both sides here, and then we will solve for the value of the n. Then we'll find a relation of the n, and the n will become 1 by 2 log in under root 10 to the power alpha s upon 10 minus 1 divided by 10 to the power alpha p divided by 10 minus 1 and divided by log, that is base 10 omega s by omega p. Now if we see, then we find there are the 4 parameters. And what are those 4 parameters? Passband is frequency, stopband is frequency, ripples in the passband and ripples in the stopband, or the attenuation in the passband and attenuation in the stopband. Now, on the basis of these 4 parameters, we can decide what will be the order of the filter. So, now the value of the n will be computed on the basis of these 4 parameters. That's why we say that if the requirement are given, if the requirement is given, then the requirement will be converted in the form of the specification. Specification means that will be described with the help of the passband is frequency, stopband is frequency, ripples in the passband and ripples in the stopband. And now on the basis of these 4 parameters, we will describe, we will decide, or we will compute the order n of the filter. That's why we have discussed during the time of the designing using a FDA, that is the filter design and analysis tool, that we have to derive, we have to compute the value of the n on the basis of the requirement or the specification. Now, if we have decided the value of the n, then we have to solve for the omega c. And how the omega c will be solved? By using the Butterworth approximation. If we solve this one, then we will find omega c is given as the omega p, and in under root 10 to the power 0.1 alpha p minus 1, its power minus of 1 by 2n. The passband specification at omega p is met exactly while the stopband specification at omega s is exceeding. Similarly, and here we can get, or we can calculate the value of the omega c either on the basis of the alpha p, that is the passband ripples or the passband attenuation, or also it can be calculated with the help of the stopband attenuation and the stopband age frequency by this formula, that is the omega c is equal to omega s 10 to the power 0.1 alpha s minus 1, its power minus 1 upon twice of the n here. Now, what we have done here, we have just considered the requirement, that is what is the ideal condition, and that ideal condition, that is the requirement, has been converted into the specification, and how the specification has been derived. That has been derived on the basis of the practical approaches, and then we have calculated here the passband age frequency, stopband age frequency, ripples in the passband, ripples in the stopband, or attenuation in the passband and attenuation in the stopband. And in the next step, that is in the third step, we have calculated the order of the n. And after the calculation of the n, the next step is the calculation of the omega c, either on the basis of the omega p and the alpha p, or on the basis of the omega s and the alpha s. So the expression for the transfer function of the Butterworth low pass filter will be described by this one, that is the omega c its power n upon s to the power n plus summation of the dl s to the power l. L starts from 0 to n minus 1, where n is the order of the filter. And what is this one? This is nothing but some constant divided by dns, that is the denominator here. And how this will be defined? This is omega c its power n divided by the poles, multiplication of all the poles here, that is s minus pl, and l starts from 1 to n. This is the multiplication of these terms here, where the pl, that is the roots, poles, will be defined by this formula, that is the omega c e to power j pi n plus 2l minus 1 divided by twice of the n, where the l is 1, 2, 3, 4, like that, integer value up to the n here. So first of all, we have to calculate the order of the n, and after the calculation of the order of the n, we have to calculate the omega c. And if we have calculated the n and the omega c, then we have to compute the roots, that is the pl, with the help of this formula, that is the omega c e to power j pi n plus 2l minus 1 upon 2n. If we see, then we'll find that these are the n roots of the unity here. And then after getting the pl, that is the roots, we will derive the transfer function of the analog filter by this representation here. So during the time of the designing of the analog filter, using the Butterworth approximations, what are the steps? First, the requirement will be given. From those requirements, we will derive the specifications. And what are the specifications? That is, what is the passband frequency, what is the stopband frequency, what are the ripples in the passband, what are the ripples in the stopband. So on the basis of these 4 parameters, we will compute the order n. And after the calculation of the order n, or the computation of the order n, next step is to calculate the omega c, that is the cutoff frequency. And after getting the value of the omega c and n, we have to calculate the poles here, the roots pl. And after getting all the roots of the pl, l starts from 1 to n, that is, we will get here the n roots. Now we can describe here the HAS, that is the transfer function of our analog filter here, and this will be described by this formula, that is the omega c its power n divided by a product of the s minus pl, where the l starts from 1 to n. So this is the description or the derivation of the Butterworth of the transfer function of the analog filter using the Butterworth approximation. Here the poles here we can see that poles are nothing but they are minus 1 to the power 1 upon 2n j omega c, that is the omega c multiplied by e to power minus j pi 1 by 2 plus 2k plus 1 divided by n, where the k starts from 0 to 2n minus 1. Now if we see the location and positions of these poles these roots, then we will find that they are at the equidistance lying on the unit circle here. Now these roots in tabular form are available, or they can be derived from the unit roots here, something like in this manner. If the order is 1, then naturally there will be 1, that is the minus of the 1, the roots will be minus of the 1, so the denominator term will become the s plus 1 here. And if the order is 2, then there will be the 2 roots. One is the minus 1 by root 2 plus minus j 1 by root 2. Similarly for the 3, these are the values here. Given for the different values of the n here, we will get here all the roots. This is the table or the tabular form of the representation of the roots here. So in during the time of the designing of the filter using the Butterworth approximation, what we have discussed today here, we are just trying to discuss the concept that how the IIR filter will be designed using the concept that the filter will be first designed in the analog domain, then that filter will be transformed into the digital domain. And for that purpose, we have discussed that we will utilize the four type of the approximation. One is the Butterworth approximation, and the second one is the Chebyshev 1 approximation, and the third one is the Chebyshev 2 approximation, and the fourth one is the elliptic or the cover approximation. And presently we are trying to cover the here the Butterworth approximation in order to design the analog filter. If the filter specifications are given in the digital domain, then those specifications will be converted into the analog domain, and then we will try to describe the passband frequency, stopband frequency, and ripples in the passband and ripples in the stopband. And on the basis of these four parameters, we will derive here the value of the n. And how the n will be described, we have derived a formula in order to compute the n that will depend upon the four parameters, that is the omega c, omega s, omega p, and alpha p and the alpha s. And after the derivation or after the computation of the order, now suppose the order is some fractional value here, then we will consider here the next higher value, next higher integer value. And after the computation of the n, our approach will be to calculate the omega c. And after the calculation of the n and omega c, we will calculate here the roots of the PL, and then we will describe the HAS. And this is the transfer function of the filter in analog domain. And after it means now we have designed the filter in the analog domain, and then by using the different type of the approximation, we will transform these specification of the S domain into the Z domain. So this is the one approach of the approximations. Having the four approximation approaches, we have discussed the Butterworth approximation that have a specialty, the linear phase response in the passband response. Here the smooth response in the passband as well as in the stopband. So in the next lectures, we will try to cover the another type of the approximation, that is the Chebyshev 1, Chebyshev 2, and elliptic approximations. And after the discussion of the all four types of the approximation, that is how the four type of the approximation will be utilized in order to design the filter in analog domain, then we will discuss the mapping, that is how the properties of the S domain will be transformed into the Z domain using the concept of the bilinear transformation. So thank you for this session. And now if you people have any query, then please ask.
Sir, when you were calculating omega c after the calculation of n, a line was mentioned that omega p specification met exactly and omega s exceeded. What does that mean?
Just coming to the point. Now, if you are interested in order to calculate the omega c, then we have used the two approximations, two formulas. One is the depending upon the omega p, and the second one was depending upon the omega s. Now, if we are aware, if we have the these values omega p or the alpha p, then we can use this one. And if we have the omega s and alpha s, then we can use this value here. In this one, the passband specification at omega p is met exactly, while the stopband coefficient at omega s is exceeding. The passband specification at omega p is met exactly. Then we will utilize this one, while the passband stopband specification and omega s is exceeding here. Now see here, you are asking something. I think you are asking what is the meaning of this one, no?
Yes, sir.
Yeah. Okay. Now see, this is the omega p. On the omega p, it is just meeting the specification of the passband. Means it is exactly this one. But means here, this is the end point of the passband. But it is the omega s. It starts, stopband starts here. So this is the H frequency from where the stopband starts, and this is the stage frequency where the passband ends. This is the meaning of that description. Okay.
Okay, sir. Thank you, sir.
Any more question? Good. So I think we have covered the designing of the FIR filter using the window method, and we are trying to cover the designing method of the IR filter using the approach, that is the how the filter will be designed in analog domain, and then how it will be transformed into the digital domain. For the purpose of the designing of the filter in the analog domain, we will use the 4 type of the approximation, and today we have discussed the Butterworth approximation for the purpose of the designing of the filter in the analog domain. Okay, so this is about the today's discussion, and the remaining 3 types of the approximation will be discussed in the next class. Okay, so thank you everybody for being with us.